Nuclear chemistry continued. Types of radioactivity. So in this module, we're going to talk about some of the common types of radioactive decay. The most common types that you need to know about are the alpha decay, the beta decay, and the gamma decay, also known as the alpha emission, beta emission, and gamma emission. And we abbreviate it with the Greek letters alpha, beta, and gamma shown here. And these three particles are all different in terms of their mass, their charge, and their general behavior. And the most obvious difference is their charge difference. And the way this was originally detected was you have a radioactive source shown on in this bottom diagram, and the source may release alpha particles in one case, and beta particles in another case, and gamma particles in a third case. And if you release these particles in a stream that flows between two charged plates, two metal plates that have an electrical charge on them, where one plate is positively charged and one plate is negatively charged, the particles or the rays that go between these may or may not be deflected towards or away from one of the plates. So if they have similar charges, they'll be repelled from the similar charge and attracted to the opposite charge. So when alpha particles were emitted, in other words, an alpha emitter, some kind of element that releases alpha particles like uranium-235, this was placed here, and what was found was that the particles deflected away from the positively charged plate and towards the negatively charged plate. And that told the researchers that this particle was positively charged. And it was soon discovered that it was in fact a +2 positive charge for this particle. When beta particles were emitted through these plates, they were deflected away from the negative charge towards the positive charge, and this told them that the beta particle had a negative charge, and in fact it was a -1 charge. And when gamma particles were released, they went straight through without being detected at all, which told the researchers that the gamma radiation had no charge at all. It was a neutral particle of whatever type. And the alpha emission, I just want to tell you, was discovered by Ernest Rutherford, who we talked about when we were talking about the structure of the atom, the famous gold foil experiment. This discovery of the alpha particle is actually what led to Rutherford getting the Nobel Prize before he did his most famous experiment with the gold foil. So, just to review, we have three types of particles. The alpha particle, now for more detail here, the alpha particle has a +2 charge. And the reason it has a +2 charge is the alpha particle was soon discovered to be helium-4, the nucleus of helium-4. In other words, the electrons are not there. It's just the nucleus. And the nucleus of helium-4 is a compact particle containing 2 protons and 2 neutrons. So its mass is about 4 mass units. That's pretty heavy for a radiation particle, and it has a large charge, +2. And we can write this in a number of ways. We can just say alpha. We can say helium with the symbol 4 for its mass number, and 2, which is the mass number, which is the atomic number of all helium. Or we can combine those two and make this symbol alpha with the 4 at the top and the 2 in the bottom, just to remind us that the alpha particle has a mass of 4, and 2 of those 4 are protons. And that's important because when alpha particles are released from some atom's nucleus, it will take away 4 particles from the nucleus. It will take away 2 protons, so the atomic number will go down by 2. And it will take away a total of 4 mass units, so the mass number will go down by 4. And an example of that is radium-222, written here, where it releases an alpha particle, written as helium-4, and the remainder is polonium-218. You'll notice the top number has been lowered by 4, the bottom number has been lowered by 2. And this is an example of a nuclear equation, which we'll talk about in the next module. A beta particle is pretty interesting, and we'll go over the details of this later, but a beta particle was soon discovered to be nothing more than an electron. However, unlike normal electrons that are found in the electron cloud, this is an electron that is formed. It is not released from the atom. It is actually formed by a neutron breaking apart into a proton and a neutron. And as a result, releasing a beta particle means you converted one neutron in the nucleus to a proton. It's like a magic change of a neutron to a proton whenever you release a beta particle. And because of that, we write beta particles either as simply beta, or we show that they're electrons, which is E with a minus sign. But because they are removing, they are resulting in a new proton being formed. In other words, you're removing a neutron and turning it into a proton. It behaves as if it has a -1 proton. Now, there's no such thing as a -1 proton, but remember, we have to keep the numbers. In order here. So if you start with, say, lithium 8 shown here, the mass number on the left of the equation must equal the sum of all the mass numbers on the right. Well, the beta particle has very little mass. It doesn't have a proton, it doesn't have a neutron, so its mass number is 0. But because you're ending up with one more proton than you started with, you're going from lithium, which is 3 protons, to beryllium, which is 4 protons, we balance that by writing the beta particle with a -1 atomic, -1 atomic number. It's not really a -1 atomic number. It just behaves like a -1 atomic number. But the important thing to remember is, if you add up the left and you add up the right atomic numbers, on the left we have lithium, which is 3. On the right we have beryllium, 4, plus a -1 from the beta particle. That also equals 3. So 3 equals 3. We're balanced between the two sides. And the idea here is that conversion, you'll notice lithium, in the original version of lithium, has a total mass of 8, mass number of 8, because it's 3 protons and 5 neutrons. But after the conversion, it's 4 protons and 4 neutrons. So the mass doesn't change, but we have changed the number of protons. And we'll talk about this later as well. So the mass, it does have mass, but it's such a small mass we don't worry about it. But it does have a charge, but we don't generally worry about charges when we're doing nuclear equations. So don't worry about the charges. Keep track of the mass number and keep track of the atomic number. Those are the two things you have to be clear on in any nuclear equation. The gamma particle is the easiest one of all. This is just pure energy. It's essentially light at a very, very high energy, and we can symbolize that as H nu, which is the Greek letter nu. This is the symbol for a photon of light. These two letters together. We also can just show it as the letter gamma in the Greek alphabet, and because it's just energy, it doesn't have mass, it doesn't have protons, it's not changing a proton into another proton, it's just being released from a high energy nucleus to become a low energy nucleus. It behaves as a 0 mass number and a 0 atomic number, and as a result, you just have a high energy nucleus becoming a low energy nucleus, but the particle numbers are exactly the same before and after. So there's no change in the mass number, there's no change in the atomic number, there's no change in the element that it is. You're just releasing energy to make it relax into a more stable form. So let's look at the different particles. We've already talked about the alpha, beta, and gamma particle, how the alpha will drop the mass by 4 and drop the atomic number by 2. The beta will leave the mass number alone, but it will, oddly enough, increase the atomic number. And a lot of students get confused by this, because you're losing a particle. How are we increasing? It's increasing because you're turning a proton into a neutron. So the mass is not being changed that much, so we still have the same mass number, but you are changing the atomic number, and that means you're changing the element to the next higher element on the periodic table. That's very odd, but you have to get used to that. And the gamma particle doesn't change the mass number or the atomic number, so that's easy. We also have protons and neutrons. These can interact with nuclei. A proton really is hydrogen 1. We can write it as H1, hydrogen 1, or we can write it as the symbol with a proton, P+, with one mass unit, mass number unit because it has one proton, and one atomic number unit because it has one proton. It is one proton, so it's 1 and 1. And if you lose a proton, that's going to drop your atomic number by 1 because you're losing a proton, but it also drops your mass number by 1. Whereas if you lose a neutron, you're dropping your mass number by 1 because neutrons are part of the mass number, but you're not touching the atomic number. So you end up with the same element, just a lighter isotope of that element. We're not going to spend a lot of time on that, but you will see in some reactions, especially later in this unit in fission and fusion, where protons and neutrons are also products along with your major product of a nuclear reaction. We also have some other particles that we're not going to spend a lot of time on. X-rays, which are almost exactly like gamma rays, but the difference between gamma rays and X-rays is very minimal. The fact is, once they're released, they're almost indistinguishable from one another. They're both high energy forms of light. They can have slightly different forms of high amounts of energy. They can have exactly the same amount of energy. They both are high levels. What makes them different are gamma rays are emitted from the nucleus of an atom. X-rays are emitted from the electrons of the atom, changing their electron level. So X-rays are not really a radioactive particle, but people group them in with other radioactive emissions anyway. But technically they're not from the nucleus, so we don't call them nuclear reactions. Positron, which we're not going to spend much time on, is an antiparticle. It's the opposite of a beta particle, which means it's the opposite. It's the antimatter version of an electron. And you've probably heard the word antimatter in a wide range of science fiction movies and TV shows and books. And you might think that antimatter is just something that writers made up. But the fact is, we've known about antimatter for almost 100 years, a little over 90 years. Antimatter has been known. In fact, the positron has been known. That's the antimatter electron. We also know about the antimatter proton. And so these particles do exist. Antimatter particles do in fact exist. They're not a figment of a sci-fi writer's imagination. These things actually exist. And in fact, you probably heard of a PET scan if you're in the medical field. A PET scan is a scanner that detects positron emissions from certain types of radioisotopes. These are injected into human beings. They're very short-lived. Within a day, they're all gone. But in the meantime, you can put these chemicals into people's bodies and watch where they go. And then you use a PET scanner, a positron emission tomography scanner, to actually visualize the release of these antimatter particles from inside a person's body. So they are quite real. We also have something called the electron capture, and we're not going to talk about this at all, so you don't have to worry about either of these last two. But electron capture means an electron from the cloud actually turns a proton back into a neutron. So it does the opposite of a beta particle. It does the same thing as a positron. Positron and beta capture both turn the proton into a neutron, whereas the one you need to know about, the beta particle, turns the neutron into a proton. And then there are other particles we're not going to talk about. There are combos of these particles in many, many cases. There are doubles in these where you might get 2 beta particles released or 2 positrons released. This happens in a number of different isotopes. But we're going to focus on the alpha, beta, and gamma. You need to know what the symbols are, the particle symbols are for proton and neutron, but we're really going to focus on the alpha, beta, and gamma here. Speaking of the gamma, let's talk about light waves and the fact that gamma and X-rays are both forms of high-energy light. And whenever you're talking about light, there are a couple different terms we talk about to describe that light. One of them is wavelength. And light can be thought of as particles. Newton was very famous for thinking of light as particles. But there was another scientist by the name of Huygens who thought that light behaved more like a wave. And in fact, now we know that light does both. It behaves like a particle and like a wave. But if we think of it as just as a wave here, a wave You can think of it in your head as going up and down. That's not exactly what the wave of light is doing, but you can think of it this way. And the distance between these crests of the wave is called a wavelength. So if the crests are very close to one another, that's a short wavelength. If they're very far apart from each other, that's a large wavelength. And shown in the bottom here, we have a long wavelength down at the bottom. Now, frequency is a term that's almost the inverse of wavelength. Frequency is how many times a wave passes through a certain point in space. So if you just put a pen down on a certain spot, say I just said right here, we want to look at this point or this point here in time, and we're asking how many waves go through. Well, this would be the first wave, and you can think of it this way. So that's the length of one wave. And some people will start it at the middle part and say this is a wave. It doesn't really matter which you count. But if you count them, you'll notice going from left to right here, in a certain period of time, we have 1, 2, 3, 4, 5, 6 wavelengths of light that have passed through in a certain period of time. Whereas in the bottom wave, this is a wave where the wavelength is much longer, but the frequency, how many times the wave goes through this point, is much lower. This one only has 2 waves that go through by this period of time. So this bottom form has a much lower frequency. The wave doesn't come through as often because the wavelength is very long, whereas the top one, the wave comes through very often because the wave is very short. So high frequency means short wavelength. High wavelength means short frequency. So they're inverse to one another. A third term we talk about when we talk about wavelengths of when we talk about light of different wavelengths and different frequencies is energy of the light. Not all light has the same energy. As it turns out, low frequency, like this bottom one, low frequency waves are also low energy. So low frequency, which is the Greek letter nu, this is actually the letter N in the Greek alphabet. It's spelled out as NU. English-speaking people and most scientists refer to this as nu. If you were in fact Greek, you would actually pronounce this ni, but we use the word nu, and that's more or less universally accepted as the pronunciation in scientific terms. The wavelength uses the symbol lambda. That's the Greek letter L for length, wavelength. So it's an L in that case, and that makes a little bit more sense. So the reason why the energy goes up with increasing frequency is because energy is actually equal to this constant H. It's actually Planck's constant, and you don't need to know this formula, just know the relationships. But the fact is, if the frequency goes up, the energy will go up. So one goes up, the other goes up. So short wavelength light, very tight waves, which have a lot of waves going through a certain point in a certain period of time, are the high energy ones. So in this diagram on the bottom here, the ones that are very tight on the far right are the high energy versions of light. Gamma rays, X-rays, these are very high energy form. If we go a little lower, we get to ultraviolet. We go lower still, we get to the visible range. And notice the visible range is a very narrow bit of the entire electromagnetic spectrum for light. We go even lower energy, we get to infrared and microwaves, and then the bottom is radio waves. And radio waves have enormously long wavelengths, tens of meters long. These can be as wide as a room or even a house. They're very low energy waves, and this is why they don't do damage to us as they go through our body. Whereas the higher energy waves can do physical damage to us, what are known as ionizing radiation. This is wavelengths of light that are so high energy, they start interacting with your molecules and breaking molecules apart. A number of different radioactive particles can do this. The alpha particles, if they're in your body, the beta particles, and especially gamma and X-ray can do this kind of damage. So X-ray and gamma rays are just high energy forms of light. And that's the real take-home message from this slide. You don't need to know the formulas. And just remember, high wavelength, so this is a high wavelength, means low energy and low frequency. And the opposite is also true. So radio waves are an example of very low energy waves. They have very long wavelengths, very short frequencies, very low frequencies, and they're therefore very low energy. So here's the spectrum shown again, and I just wanted to show you the hard X-rays and what are called the hard X-rays and the gamma rays really share the same range of energy. So they in fact are exactly the same types of photons of light, particles of light, waves of light. They just are emitted in different ways. Gamma rays from the nucleus, X-rays from the electron cloud of the atom. So they're not really nuclear in origin. And here is a chart of nuclides, all the nuclides known, 3,339 known isotopes of the 118 elements. And this is a chart, and these charts are plotted in different ways. You'll see different versions of it. But this chart on the y-axis, you see vertically, is the number of protons. In other words, the atomic number. So as you go up the chart, the atomic number is getting higher. You start down here at hydrogen, and you go all the way up to the top to 118. That would be oganesson. And so there are your 118 elements. But remember, there are lots of isotopes of each element. Most are man-made. And every little box, every little pixel in this represents a different nuclide, a different isotope that is known today. And they're color-coded. And you'll notice the black ones represent the stable isotopes. These are the naturally occurring isotopes that are not radioactive in any way, and they will last literally billions of years or even longer without changing. They're extremely stable. And you'll notice there are only a few of them in here. Very few of the isotopes that are known today are stable, but these are the ones that came with the Earth when we got it, and they're very stable isotopes. But there are a lot of other isotopes, and they're color-coded by the type of radioactive decay they undergo. And I mentioned the y-axis are the number of protons. The x-axis are the number of neutrons. So they get heavier and heavier as you go to the right, and as you go up. So elements at the top part here have the highest atomic number, but also the highest mass number, whereas the ones down here are the smallest isotopes, the smallest nuclides. And you'll notice that the ones that have a lot of neutrons, because they're over to the right, they lose neutrons. That's their main form of decay. The ones that have too many protons, the ones that are really high on this graph, the brown ones, they will lose protons to get rid of it. Now, we're not going to focus on these kinds of decays much, but you'll notice if they're very heavy elements up here, and they have too many protons and too many neutrons, they're really up high and they're far to the right, they're going to lose alpha particles, which are essentially 2 protons and 2 neutrons together being lost. Whereas these light blue ones represent elements, remember over here is a lot of neutrons, they represent too many neutrons. Well, one way to get rid of neutrons is to release beta particles, which turns neutrons into protons. So elements here will become elements over here. And if there are elements over here that have too many protons, well, they can be converted to neutrons by positron decay or electron capture, which you don't have to know about. But the point here is that different points on this will have different modes of decay. I'll point out one more. SF stands for spontaneous fission. Fission means the atoms are so large they'll split apart. Sometimes if they're hit with something, sometimes they'll split apart on their own. And SF means spontaneous fission. So these elements up here in dark blue are so big, they're so massive, that they're just not stable at all. And they'll split into two smaller elements, 2 smaller nuclei, and maybe some extra neutrons and even some protons on occasion. So you get all these different modes of decay depending on what it is. Now, you'll notice gamma is not mentioned here because so many of these also release gamma particles that they didn't color code it for gamma. But with this, we'll stop here.